Good morning, everyone. Welcome to the Badger Dairy Insight. Thank you for joining us today at this month's University of Wisconsin Division of Extension Badger Dairy Insight. It's a monthly webinar series offered on the third Tuesday of each month. The Badger Dairy Insight provides the latest research, dairy-based information to improve animal welfare, breeding and genetics, selection, automation and modernization, and nutritional decisions for producers, dairy workers and managers, and agriculture professionals. My name is Erica Bierstrom. I'm the Regional Dairy Educator for Brown, Door, and Kewaunee counties, and I'll be your host today. We hope this is an opportunity for informal discussion on today's topic. Since this is a webinar format, please add any questions or comments in the Q&A button at the bottom of your screen. This is a webinar and it is being recorded, and we will send you a link to the recorded webinar within a week in hopes of you sharing it with others you work with. Our speaker today is Dr. Nesli Akdeniz. She is an assistant professor and extension specialist in biological systems engineering at the University of Wisconsin-Madison. Her research and extension program focuses on livestock housing, energy-efficient ventilation design, and air quality. She conducts computational fluid dynamics, CFD studies to stimulate microclimate conditions inside agricultural buildings. Her approach to ventilation design is holistic, considering not only heat stress, but also energy use, noise levels, and access to natural light. She teaches BSE 367 renewable energy systems, where she often incorporates sustainability concepts into her research and extension efforts. In today's presentation, she'll introduce a new online calculator designed to support ventilation decisions in dairy barns. The presentation will conclude with a comparison of weather data from 2000 to 2004 and 2020 through 2024, highlighting how ventilation needs to have changed over the past 2 decades in northern and central and southern Wisconsin. And with that, I will hand the presentation over to Nesli.
Thank you very much, Erica. Thank you. And thank you for joining us today. My name is Nesli Akdeniz. As Erica introduced, I'm an assistant professor and extension specialist in biological systems engineering. So we will dive into dairy ventilation design today. So let's start with some very basics. So when we think about ventilation design in dairy buildings, the most common designs that are coming to our mind are natural ventilation. We see many of them, tunnel or hybrid. So sometimes we have a naturally ventilated building and we are able to add some exhaust fans, then it becomes a tunnel ventilated building, or it becomes a hybrid ventilated building. Hybrid, we can use mechanical ventilation in summers during very warm days. And when it cools down, we can just shut down those fans and it can be a naturally ventilated building. And cross ventilation, we don't see that often, but we have some very state-of-the-art cross ventilated dairy buildings in the state. So this is an example of naturally ventilated building. This is a fabric barn. So you can see very steep roof, 612, and the fresh air comes in from the side walls, big openings on the side walls, and then it just exits from the ridge vents. So this is a facility so that you can still see the circulation fans, but there are no exhaust fans, there are no supply fans. There is no mechanical ventilation fans. So it is very bright, very quiet, much more like a greenhouse than a livestock building. So it does work for this farm. So this is a very good example of cross ventilation. So this is one of the newer buildings. So it is actually state of the art. Maybe it's a little bit difficult to see, but you can see the ventilation fans at the very end. We have the circulation fans. We also have the exhaust fans that are placed on the roof. Plus the pressure tube ventilation, we call it PPTV. We usually use this one for calf buildings, but it can be also used for lactating cows. It's not that common, but it's possible. Here you see a different version of PPTB. This is a research we are conducting in Arlington Research Station this summer. So when we think about PPTB, what is coming to our mind is a fabric tube with holes on it. So this is a different version of it. Instead of a fabric tube, we have a solid structure, and we have the tubes coming out from that solid structure. So there are supply fans. They provide fresh air to the solid structure, and the fresh air comes out from those tubes. So we are ventilating. We are not ventilating the whole barn, but we are ventilating where the cows are located, where it matters the most. So, what motivated us? So I wanted to talk about this a little bit before we dive into the calculator. So, what motivated us? Why did we develop this online tool? So, we looked at the weather data in Wisconsin. So, there are different regions. According to one source, it says there are 9 different climate regions in Wisconsin. But when we look at the big picture, we can separate it into 2 regions, northern or central part of Wisconsin. So this part, it is a little bit cooler summers, and the southern part of Wisconsin, where we are located in Madison area. So this is a little bit warmer or more humid summers. And then we looked at the weather data over the last 20 years. So we checked the weather data on average from 2000 to 2004 and compared it to 2020 to 2024. So last 5 years and 20 years before that one. And whenever the ambient temperature was over 20 degrees C, so it corresponds to 68 degree F, we called it is a summer day. So if it is between 4.4 and 20 degrees C, we called it a transition day. So it is a fall or a spring day. And when the temperature drops below 40 degree F, 4.4 degrees C, we called it winter. So we looked at the data. So we looked at the southern region and a little bit northern or central region. So as you can see here, let me see if I can get my pen. When we look at the medicine data, so 20 years ago, there were 68 summer days, and the number increased to 85 in the last 20 years. So when we look at the transition days, so it was 163 on average. Now we have less. So when we look at the winter data, so winter data, maybe we need to dig into data a little bit more, but it is pretty stable. So this is for the medicine region. Then we have for the central region. So again, 57 to 71, there is a little bit increase. And 157 to 144, there is a little bit decrease. And 151 to 150, so it stayed pretty stable. So what we are seeing is we are seeing 25% longer summers. So number of summer days increase. We see a shorter transition period. So if we call it spring or fall, number of spring and fall days decrease, and winters are mostly stable. So one, weather patterns are changing, right? There are seasonal changes. Two, we do have the wind shadow effect, right? So, for example, this is a farm that we are working with. So they used to have maybe 1 or 2 buildings, but this farm is growing and they keep adding buildings. And in an ideal world, we add buildings parallel to each other, right? But in reality, it's not possible, right? There are a lot of logistics. So, for example, if you have a building here and if wind is blowing from the southwest direction, so this building here, it shows us it blocks the wind coming in and it's causing a wind shadow on the barn that I circled here. So one is the development of the farm, like we have more buildings around and it doesn't let that wind to reach sometimes to our buildings. And then another factor, wind shadow is not always outside of the building. Wind shadow is sometimes inside the building. So, for example, we have more robots inside the buildings. Right here, we see the AMS units. So, if they are put in front of an air inlet, they do block the air coming inside the building. So, here we see a simulation of the barn. So let me see if I can make this work one more time. Here we have the supply fence. So this is our air inlet. And here we have our exhaust fence. So air moves this direction. So here we have the AMS units. So I show them here. So air moves, and then we have the circulation fans. We still have those big circulation fans. And then you can see this first row, which is usually the luckiest row, since they are very close to the air inlet. There is a big wind shadow effect there. So we are looking at the velocity data here. So these dark blue colors, they mean low air velocity. So we want to see much more like lighter blue or maybe greenish colors, especially at cow sitting height. But these AMS units are causing kind of wind shadow inside the building, not just outside of the building. Yeah, my computer is a bit slow. Okay. All right. So, and then we see larger buildings, right? So maybe it used to be only 4 rows, maybe 6 rows. Now we see very, very large buildings. So there are still places natural ventilation works. So I am not saying we should all switch from natural ventilation to mechanical ventilation. For example, this is the barn that we visited. This is the fabric barn. This is where it is located. So there are no wind shadows around, right? So it can capture all the natural wind that is coming in. And then they have very steep roof and so they have big wide opening side walls. So natural ventilation works for that farm, for that specific building. But nowadays it doesn't work for all buildings anymore. So basically, due to changes in the seasons, since we have larger barns, and due to all the development, rural development, and having more and more buildings around, and wind shadow effects. So it was our motivation. So if we want to switch from natural ventilation to mechanical ventilation, here's an online tool that is available. And here we see the two links, and then I will explain the difference between them. So our link is go.wisc.edu/coolcows or go.wisc.edu/coolcows2. And this is how it works. So step number one, we need to choose a location. So once we choose the location, there is a map on the calculator and it highlights that region. So I will show you the calculator in a minute. It is ready on my other screen. So either we are going to say we are the southern part or we are in that central part or the northern part. So two climate regions. Then we need to enter barn dimensions. So some numbers are entered in the calculator. So these are just examples. So kind of space saver for you. So to be able to present as an example, we enter these numbers, but you need to enter your site specific information. So we know the width, barn width, right? We know the lanes, they are easy. But if you ever like confused what was the sidewall height, what was the ridge height, there's a small figure, small schematic here. It reminds us the sidewall height and the ridge height dimensions where we need to look at. Number of cows. So one important part of this calculator is it assumes that there is no overstocking. So the reason we are asking, so this specific barn volume is able to accommodate this many heads. So we have this many stalls and this many cows, and there is no overstocking. So the reason we are asking number of cows is so that we can estimate energy consumption per head to be able to make some comparisons. So it's the main reason that we are asking number of cows. Air exchange rate. So the recommended air exchange rate in summer for lactating cows is 60 air exchanges per hour. So if you have a different number in your mind, so 60 has been already entered in the system. But if you have a different number in your minds, for example, if you're not talking about lactating cows, if you're talking about dry cows, if you want to enter a number like 50 air exchanges per hour, you're able to do that one. You can just change that number. And then fan capacity and fan price. So this is the difficult part, since we need to have an idea of what type of fan we are going to purchase. And it requires a little bit of research. So we need to go to the fan companies' websites and search what kind of fans are available, how much they may cost. So I understand this is the difficult part, but the calculator cannot do this part for you. So it needs to be like, there needs to be a little bit background information here. And then when we have the fan information, one important part is fan efficiency. So when we are thinking about fan efficiency, so please ask that company best lab report. So the report looks like something like this. But when we are thinking about fan efficiency, please do not look at the fan efficiency at zero static pressure. There is no building with zero static pressure, right? Static pressure is the resistance to flow, airflow. So anything inside a building increases static pressure. So we have cars, we have stalls, we have baffles, we have robots, we have people working, anything increasing static pressure. So static pressure is never zero. So please do not look at the fan efficiency at zero static pressure. If you don't know the static pressure inside your building, a good estimate would be 0.05, 0.1, or 0.15. So you can pick up one of these numbers. If you want an average number, 0.1 might be a good number to start with. And then we enter that static pressure, that fan efficiency at that static pressure. And we get the outputs. So voila, it works, right? So it gives us the number of fans required and total fans. So we just enter the price of a fan. So it just multiplies it. One thing that is very, very important is it gives us the required inlet size. So the inlet size is too small, then it increases static pressure too. So assume that you have exhaust fans and you don't have enough air inlet, so that exhaust fans will have a very difficult time pulling the air through your building. So you need to have the correct inlet air size. So this is the minimum inlet size. Less than this one will put more pressure on your exhaust fans and lower your fan efficiency. So it estimates your monthly energy consumption. It also estimates your annual energy consumption. And then by just dividing that number to number of heads you have, number of cows you have, it estimates per animal energy, per head animal annual energy consumption. Okay, so let's look at an example. Erika, this is the part that I will ask your help if you can see my screen, if it followed me or not.
It followed you. If you can make it a little bigger, that would be great. Excellent, right there.
So as I said, some numbers are entered. So you can, these are just example numbers. It will not apply to your building, but just as an example, right? So first step is we will choose our location. So as soon as I choose the location, it will highlight. So if I say two of them, it will give me a warning signs. Please choose one. So I need to choose a location. Then we can change these numbers. You can enter anything you want, then it will adjust the calculations, but we will keep it for this example. We have the width, we have the length, we have the height and the sidewall height, number of cows, right? Here, assuming there is no overstocking, there is sufficient number of stalls per number of head we have inside. Air exchange rate, as I said, 60 is a good number for lactating cows in summer. So if we want to change it to 50, if we have dry cows, we can. But for this example, we will keep it. Fan capacity and fan price. So this is the information this is the difficult part, right? As I mentioned, so this is the information that we need to gather. We need to do a little bit research. And fan efficiency, so we can see an example here. So we are not going to assume static pressure is zero. We are going to make an assumption. We will say our static pressure is low. We don't have any baffles maybe inside this barn, so it is 0.05. Or it's a little bit a little bit higher than that one. We have baffles, we have cross ventilation, so maybe it is 0.1, maybe 0.15. Usually static pressure doesn't go above 0.50. And then we are going to enter that fan efficiency. So the advantage of this tool is we can play with our numbers, right? So when we look at the website, if there is there are different options. If more than one pen is available, right? One of them is this, for example. Probably the pen price will be a little bit higher than this one, but as an example, I entered the lower price. But let's say these are our settings. We need 18 pens. Okay. And it costs us $9,000 to purchase these 18 fans. And the annual energy consumption per head is 443. Okay. Let's say there's another model available. Let's say it has a little bit higher capacity. So since it's a bigger fan, let's say it is more expensive. And then usually larger fans are more efficient. So the smaller the fan gets, usually efficiency goes down. So we can assume maybe it is a little bit more efficient. So we needed 18 fans. Now we need 15 fans. So we can think about the space that will take. So do we have enough wall space to put 18 fans, or does it make more sense, although these are a little bit bigger fans, to have 15 fans? Since if it is tunnel ventilation, usually our space is limited on the wall. So we are putting those fans on that short wall, right? So there isn't usually enough space. So sometimes thinking about it, like maybe we don't buy this model, but we buy this model, then instead of 18 fans, we need 15 fans, but we will have enough space. It may help. So the total fan cost didn't change, right, for this example. But when we look at this number per head energy consumption, it used to be 443. Now it dropped to 417. So 6% decrease, right? Energy consumption. So we save that much energy, that much ventilation, electricity, energy consumption since our efficiency went up, since we prefer the little bit larger fan. So this calculator allows us to play with these numbers. And most importantly, it gives us the required inlet size And I have seen buildings, they do not have the correct inlet size, and they have many, many exhaust fans. Even as when you visit, it's difficult to count. They have more than maybe 30 exhaust fans, but they don't have the enough inlet size. So those exhaust fans are kind of having difficult time to work. I will pull this one here. All right, so it is following up, right, Erika?
Yes, we're back at
All
your
right.
screen, your PowerPoint.
So one of the limitation of this calculator is we are assuming that we can achieve 60 air exchanges per hour, right? The whole calculations are made based on that assumption. But based on the model or fan capacity that you will use, you may not be able to achieve exactly 60 air exchanges per hour. It might be 62 air exchanges per hour, or it might be 57 air exchanges per hour. So after designing your mechanical ventilation system, if you want to test that system, how it is performing, we have the second version of the calculator. So we call it Cool Calves 2, so number 2. We can come to this calculator and we can enter. So this is a little bit different version. So we are entering how many fans we have. We are entering our fan capacity, and it is giving us the air exchange rate. So it's just doing the same calculation, but in a little bit opposite order, so that we can see how your system will perform. Or if you already have a mechanical ventilation system, you can just check how it is performing. So this is kind of evaluation or assessment calculator. So again, it will give you the required inlet size. You can compare it to the inlet size you have. So if your inlet size is too small, if it's bigger than this number, larger than this number, then it's good. But if it's smaller than this number, it means that your fan efficiency is not the fan efficiency that best lab report gives to you, right? You have higher static pressure inside your building. And even like you may be able to, it is usually difficult to understand how much ventilation fans consume electricity on a farm. We have a rough estimate, but unless it is on a different bill, it's difficult. But you may even be able to compare in theory how much these fans are supposed to consume versus in reality how much they are consuming. So if they don't match, then it means there's a problem with that mechanical ventilation system, or there's some room for improvements. All right, so we looked at this table, right, at the beginning of presentation. So now we saw the calculator, we looked at these numbers. Can we go ahead and calculate the energy consumption, annual energy consumption for a farm, and how it's changed over the last 20 years? So if we make a couple of assumptions, we can, right? Just for the comparison purposes, we will make a couple of assumptions. So 60 is our magic number. By now we know, right? 60 air exchanges per hour in summer, 4 air exchanges per hour in winter. These are our kind of magic numbers we enter in all calculations. And then what happens in between, right? Okay, winter, summer. Are we going to assume an average number? Are we going to say 40 air exchanges per hour? Or in this calculation, just for the calculations, we assume that we adjusted the air exchange rate in 5 intermediate steps between 60 and 4. I mean, in reality, in a working farm, there is no way we can control ventilation this accurately, right? Not like 5 intermediate steps, but to be able to compare data, to be able to make a fair comparison, we made this assumption. And electricity rates, I searched this one a lot. It really depends where you're located, what kind of, location it is, region it is. But let's assume it is around 7.2 cents per kilowatt hour in 2004, like 20 years ago. And now it is 12.85 cents per kilowatt hour, like as of last year. And there's inflation, right? So over the 20 years, everything has changed. And we can assume a number. We can use the consumer price index to take into account the inflation rate. So here's our calculation. So over the last 20 years, so you remember this number, right? This is the number we saw on the calculator, 443 kilowatt hour per head right now in 2024 to be able to, this is only taking into account mechanical ventilation. It's not taking into account circulation fans. So to be able to mechanically ventilate that building, we need to spend this much energy. So if we multiply it with the electricity rate, we will end up with a cost like $57 per head. And then, so there's no inflation, it's already 2024, so it will be $57 per head. But if we do the same calculation, if we go back for Madison area, our number will be 417. And then before we are adjusting for inflation, it will be a number like $30. And then once we adjust it for inflation, it will be a number like $50 per head. So over the years, over the last 20 years in Madison area, in southern part of Wisconsin, so it increased the energy consumption or electricity cost increased 14%, and in the central or northern region, it increased 11% per head. So it is getting more expensive to ventilate those buildings, basically due to changing weather patterns and due to maybe we took into account inflation, but changing electricity rates, right, due to those two reasons. Now it is much more expensive to ventilate a mechanically ventilated building. So it is very important that we enter all our numbers correctly and design the system in an efficient way so that it doesn't cost us more in the future. All right, so we assume that there is no overstocking in this calculator, and I wanted to prepare just two slides to show you how overstocking affects ventilation. So overstocking, so in this study, what we did, we adjusted the ventilation rate. So we cannot simply say, okay, we are going to put more number of animals inside this building, but let's increase the ventilation rate a little bit. So it doesn't work like that. So the assumption here is we have one animal per stall. If we are going to overstock, yes, we may be able to increase the overall air exchange rate or ventilation rate, but then still there will be some, stagnant zones inside those stalls. Animals will serve as a block, right? Will block the airflow and it will not let the air go through. So what we are seeing here is we are seeing 100% occupancy rate. So I'm not saying 100% overstocking, 100% occupancy. So number of cows is equal to number of stalls. Here we are seeing 80% occupancy. So we have less cows than the number of stalls. So we are looking at the temperature data here. So here we want to see dark blue, like cool zones, cool colors. So greenish, blue, light bluish, those aqua colored parts of it means it's warming up. So as you can see, there is a difference, right? And ventilation rates are adjusted. So 100% occupancy rate, it has higher ventilation rates. So although ventilation rate increases, the temperature inside the stalls, it increases. Since it is not that simple, we cannot just say, okay, let's add one more fan, we can increase the stacking density. So let's look at another example. Now we are looking at 120% occupancy. So it is 20% overstocking, and this 100% one is the regular one. So as you can see, the colors are they are changing, right? So instead of having this darker blue, now we have lighter blue, greenish, much more like aqua color, which means inside the stalls is warming up and our ventilation system is not working that efficiently. So if we are planning to put more cows inside the building, I do understand there are some needs, and sometimes it needs to happen. Then the ventilation design needs to change to be able to take that into account. So maybe we need more circulation fans, maybe we need a different system of ventilation. So just adding more ventilation fans or exhaust fans, or just by increasing their capacity, we are not able to avoid some of the problems we see here. All right, so ventilation. So here I kept saying 6 air exchanges per hour. So this is our magic number, and we are thinking about heat stress, right? So we don't want these cows to be stressed. We want them to be comfortable. So we always are talking about temperature, and maybe we are a little bit referring to humidity. But ventilation design is more than these two, right? It's not just temperature, humidity. We have air quality inside. So we have the noise levels when we are buying these fans in the catalogs, right? They give that noise level that each fan is causing. So we may be able to check those noise levels and light, how much light we are receiving based on the ventilation system we choose. And sometimes people say, what's the relationship like ventilation and light? And I will show you an example in a minute. Okay, so noise levels, we want them to be below 85 decibel. So prolonged exposure above 85 decibel is not recommended. So one way is to check the catalog before we buy the ventilation fan. And if there is a less noise option, if the decibel is lower, and if the price is correct, it might be a fan that we may prefer to purchase. So there are some numbers. We did a small study. We measured the noise levels. So circulation fans are usually below that 85 decibel threshold. Low capacity supply fans are also good. Some high capacity exhaust fans, some may be very large fans, or some fans that are not maintained well, they may exceed that level. And if you have animals sitting just next to those exhaust fans, or if you're spending significant amount of your time as a worker close to those exhaust fans, it might be something that you might want to pay attention. So it's very easy. So there are apps. There is an app from Nayash which you can use. There are some, smartwatches. They measure the noise level. You may want to buy a very, very inexpensive noise meter, so decibel meter. So you can just measure the levels, and then you can use it as an indicator. If there's a change, it means that the fan may need some maintenance, right? The change in the noise level may indicate poorly maintained ventilation fan. If it is less than that threshold, then you're fine. But if you're coming close to that threshold, or if you feel like it bothers you, then it is time to take an action. And then the lighting level. So what we want is there are studies, or there isn't a very recent study, but there are some studies in the past. They report that we want 200 lux at the cow eye level. So this is not super bright, actually, like probably my office today is brighter than this one, but we don't want them to be in very dark condition, especially during long winter days. So it does affect with their metabolism. So how is it related, right? So ventilation and lighting. So we visited several farms, and we did measure the light levels inside these buildings. So if it is a naturally ventilated building with rich vents, right, those windows on the roof, they help a lot. They are naturally very bright. So if it is this kind of building, you may want to turn off your lights to save some energy since it is already bright inside. So if you're talking about 200 lux, the levels we measured, they were about 1000 lux. So naturally, they are bright. But if we are talking about a cross-ventilated farm, the right picture here, the picture on the right, so we have one big air inlet, right? So this is where it is bright, but as you go through the barn, especially if you have baffles that are blocking the light coming inside, it's getting darker. So there might be some dim spots inside your building that cows are not getting enough light. Then you need to supplement it. You need to use maybe artificial light, or you need to make sure your lights are on during especially those cloudy days. They may not be getting enough light. So it is kind of related. It is kind of like related to each other. Okay, so this is kind of a summary of what we found. So, for example, office lighting is, they say 300 to 500 lux. We are looking for 200. So we visited many naturally ventilated or hybrid ventilated buildings. So they were all about that 200 lux threshold. So cross ventilation, especially as I said, if they have baffles, then they may be less bright, or like in one case, the lights level dropped below 200 lux threshold. If it is the case, just be aware. Or when you're developing this ventilation design idea, or like when you are thinking about mechanical ventilation, what can be done? So if we have that rich vent, although we don't use rich vents that often anymore, right? Having that one, it helps a lot, especially during long winter days in Wisconsin winter. All right, so with that, I will stop here and then I will open it up to questions.
We don't have any questions in the Q&A yet, but I have a couple of questions. So is this only available? I know obviously you work for Wisconsin and you made this for Wisconsin farmers. Is this only available to Wisconsin farmers? I mean, outside, or are other people's areas available on this app?
So
Can they select other areas?
yes, calculator is available to everyone. It's free. You just need to go that link. It's very easy. Go that list.edu//cool cows or cool cows too. So it is open to everyone. So it does apply. But the only difference might be the region, right? So we selected the northern region, southern region. So maybe we can think about the north central area, so where we are located. So it will apply. So you can choose northern or southern region based on your location. So if you're much more like Minnesota side, maybe the northern region. If you're like Illinois side, maybe the south.
So, eh, for instance, if a farmer from Missouri, for instance, wants to try to use it, that's, I guess, closer to southern Wisconsin, but it's not necessarily going to apply to their area. in weather-wise.
Yes, that's
Okay. All right.
yes.
That's good to know. So the other question I had is how easy is it to print out the report? What does the report look like that they would hand over to their salesperson or whatever from the fan company or distributor?
So it does the calculations immediately. As you can think it about like a Excel spreadsheet, right? So it does the calculations. You can get a print screen, or you can just go ahead and print it as PDF, so that if you want a report to be printed and to have it in your hands, those are the options.
Okay. I don't see any other questions out there. Do you have anything else you want to throw in here at the end here, or any other points you want to bring up?
Yeah,
Erica,
Yes,
there is a question.
I do not see the question.
Oh,
Would you read it for me,
um,
Jackie? Go ahead.
yes. Are Wisconsin dairy producers regularly overstocked? What adjustment would you make to your 60 ACH input to make sure you have adequate ventilation with more cows?
Yes, it's the reason I overemphasize, right? So this calculator is not designed for overstocking. So I think it can tolerate some, maybe 20% overstocking. It may be able to tolerate that one. But if we are talking about very high occupancy rates, like if we are talking about 150, 160% overstocking, then this calculator will not work for that. So overstocking, it comes with its own challenges, right? So I do understand the construction costs are so expensive, right? So we have to do what we have to do, but it comes with its own challenges, and maybe 20%, 30%, they are tolerated, but over that one, then we need a different mechanical ventilation system. We need a different design, actually. So this calculator will not work if we are significantly overstuffed.
Okay.
But yes, I am aware it's the concern, and there are many concerns, right, with this having robots inside so that animals are more independent. So we have a little bit more flexibility. We can overstock a little bit more nowadays compared to the past. But the building design, ventilation design, there will be some challenges.
All right. So Jackie, I cannot see the question. So do you see any others before we wrap
No,
this up?
that was the only one I see.
Okay. All right. So I'm going to have you bring up your slides again real quick, Nestle, and advance to the next
Okay,
section. Just those last couple of slides.
all right. So please reach out if you want to try it, and if you want me to walk you through this calculator, I will be happy to do that. And then let me share my slide one more time.
All right. So I hope you enjoyed today's webinar and focusing on the energy efficiencies of dairy barns. Join us next month on September 16th for boosting fertility of dairy cows through better semen handling. And join Extension educators Heather Schlesser and Ryan Steery right there on the slide, as they will walk you through the steps of critical proper semen handling to improve conception rates in dairy herds. And for additional information, please check out university-based resources. Please visit the University of Wisconsin Extension Dairy Program at dairy.extension.wisc.edu or find us on the Extension Agriculture Facebook page. So with that, thank you very much, Nestle. And thank you everyone for joining us today. I hope you learned a little bit, and I know Nestle would be happy to answer questions on this particular tool. She's been very excited about it and really helping us promote it with farmers, and we've tested it with some farmers, and so far it's been a big hit and everybody has found a lot of value in it. So please check it out. All right, everybody, you have a great day.
Thank you. Mhm. All right. Thank you so much.